Captain's log, stardate 47993.0. The Enterprime has barely survived an unprovoked skirmish with the Composite Empire, and we're in dire need of repairs. Mr. Littig, please set a course for the nearest starbase.
Aye, aye, Captain. And I should add, I use that term with all the respect due to other famous captains, like Captain Crunch or Captain Underpants.
I don't need the sarcasm, Lieutenant. Just set the course.
Aye, aye, Captain. Inputting the 4-digit navigational coordinates now.
Red alert. Red alert.
Computer, status report.
It would appear that there's a supermassive black hole in this sector, and, just dumb luck, after I applied the navigational algorithm to the 4-digit coordinate Pete set, we ended up on a course right into the heart of it.
Okay, so, all we have to do is choose a different 4-digit number to start with.
That should work. That should work, Captain.
Make it so.
Completely different seed number selected, laying in the course, Captain.
Computer?
I'm confused, Captain. We appear to be on the exact same course that we were on last time, directly into the black hole.
Mr. Littig, get us out of here, now!
Resetting course, Captain.
Well, that seems better. What's our ETA at the starbase?
We should be arriving in...
What now, computer?
You're not going to believe this, but we're heading straight for the black hole again. It seems that no matter what starting number Pete chooses, we always end up getting pulled right into its gravity well.
Alexa, end program.
Jeez, Pete, what'd you do that for? We weren't in any real danger, it's just a holodeck simulation.
I know, but I figured out the problem, and we weren't ever going to be able to get out of there alive. It was a real Kobayashi Maru situation.
What do you mean?
It was something Alexa said that made me realize what was going on.
You're welcome.
I'm totally lost. Can we get back to the simulation?
No point. It won't matter what number I choose to seed the navigation computer. We're always going to end up on the same trajectory, heading right into Kaprekar's black hole.
Who's Kaprekar?
Alexa, new simulation. Put us in the math club living room. Oh, and snack bowl. Prechos, hot.
The living room? Dude, we could have just walked out the door and been in the real living room.
Yeah, but this way we don't have to make the Prechos before we can start.
Start what?
Oh, you're going to love this one. Have a seat. I want to tell you all about a cool little math nugget called Kaprekar's constant.
Black hole sun, won't you come? Wash away the rain, black hole sun.
Hey there, Math Club. Welcome to another episode. It's been a little while since our last one, and we're excited to be back. And to tell you the truth, this one's a little special, isn't it, Pete?
Yeah, that's right. You have been out visiting me. You are in town from California. We recorded a little promo a couple days ago, and you're still here. So we thought, why not do an episode of the show?
But the ironic thing, everybody, I want you to picture this. We are in the same house together, but we could not find a good way to make it work so that we could be in the same room while we were recording. So Pete's upstairs in one room and I'm down in the living room. So it's almost like I'm back at home.
Yeah, and from my point of view, it actually feels identical because I am in my standard location. I can't hear you in real life. You might as well be in California.
I might as well be, but it's still fun to be here. So why don't we jump right in? You started talking about something called Kaprekar's constant. Get us started with that, Pete. What is it?
Yeah, well, as you know, I spend most of my free time just sitting around thinking about what Noah and I might talk about in another episode. And I was kind of running some number theory through my head, and I saw a little video that got me thinking about a little trick that you can do with 4-digit numbers. And before I tell you exactly what's going on, I thought, why don't we take a 4-digit number and do a little math on it and see where it leads?
All right, I'm game. How do we get started?
Why don't you pick a 4-digit number? anything you want.
Any number I want?
2319! We have a 2319!
All right, because I have a super huge ego, I'm going to pick my birth year. Let's pick 1971, 1971.
Dude, I don't want to contradict you, but you picked my birth year.
Well, that's because you also are a huge ego.
Oh, I forgot. You're right. I forgot. Okay. 1971. That's a totally good starting number. Now, that number has 4 digits. And what I would like you to do is to rearrange them so that we create a new 4-digit number where the largest digit comes first and then the second largest comes second and so on down the line.
Okay, so 1971 has a 1, a 9, a 7, and another 1. So I'm going to arrange this 9711, 9,711.
Awesome. So let's put that off to the side for a second. Now do the same thing, but arranging the digits from least to greatest to create another 4-digit number.
All right, so instead of 9711, I'm going to reverse that. It's going to be 1179.
Perfect. So now we've got 2 4-digit numbers. I would like you to subtract them, the smaller from the larger.
All right, let's see here. 9711 minus 1179 is 8,532.
Perfect. Now I'm going to ask you, can you please repeat the process?
So I'm going to take the digits 8532 and arrange them in decreasing order and increasing order and subtract again.
You got it.
All right, so that is already in decreasing order, 8532. So that'll be my larger number. The reverse of it is 2358. And when I do the subtraction, I get 6,174.
Perfect. Now, please repeat again.
Dude, how many times are we going to do this?
All the live long day. This is the show. We're just going to keep going and going. I'll tell you what, this will be the last time.
All right, so I have a 6, a 1, a 7, and a 4. So that's going to give me 7641 minus 1467, which equals, oh, look at that. It equals 6174 again.
It does. And if you were to do this again, obviously, you would repeat the exact same subtraction problem and you would get another 6,174 as your answer.
All right, and what is this supposed to be showing us?
What this is illustrating is a fact that is true about nearly every 4-digit number. Namely, if you start from a number with 4 digits and you perform this repeated subtraction process, you will always, inevitably, without fail, end up at 6,174.
Well, that's neat, but I'm going to back up a minute. You said nearly every 4-digit number. Why is it nearly everyone? And what's the difference with the numbers where it doesn't work?
Let me give you an example and then we'll see what happens. Okay, so please start with the number 3,333.
Oh, yeah, I can already see the problem here. I'm going to be subtracting 3333 from 3333, and I'm going to just hit 0. So I guess any 4-digit number where all 4 digits are the same is not going to work.
Those 10 particular numbers, starting with all zeros and then ending at 9,999, those 10 4-digit numbers are off limits to us. They will always end up at 0, exactly like you illustrated. But if we pick any of the other 9,990 4-digit numbers, we will invariably end up at 6,174.
I think you miscounted, though, because there are only 9,000 4-digit numbers. They start at 1,000 and go to 9,999.
That's technically true. So let me clarify. There are 999 other numbers that, while strictly speaking, are not 4-digit numbers in the usual sense. We can still use as 4-digit numbers here while running through this Kaprekar process.
What numbers are those?
Well, if you take any number with 1, 2, or 3 digits, you can turn it into a 4-digit number by adding leading zeros at the beginning of it.
Oh, okay. So 1 would be 0001, and 65 would be 0065, that sort of thing?
Exactly. And if we were using 0065, i.e. 65, we'd end up with the subtraction problem 6,500 minus 0056, or 6,500 minus 56.
Okay, that makes sense.
And if we compute 6,500 minus 56 and then keep repeating the process, we'll eventually end up at 6,174, just like every other four-digit number.
Well, I want to put that to the test. Can we try it with one more number?
Yeah, please do. You started with 1971. Let's try something else.
Okay, this time I'm going to pick my daughter's birth year. She was born in 2001, so 2001.
All right, let's go ahead and do it with 2001.
So my first step is I'm going to rearrange this into 2100, 2100, minus 0012, or 12. So 2100 minus 12 is 2088.
Perfect.
And now I'm going to repeat the process.
You are.
All right, so that's going to give me 8820, 8820, minus 0288. So 8,820 minus 288 equals 8532. Hey, wait a second. We hit that same number when we did my birth year, 8532. We already know where this is heading. The next step is going to be 6174.
That's right. You started with a different number, 2001 in this case, and you ended up at 6,174. It's sort of like 6174 is this black hole that is pulling all of the other numbers into itself.
That's interesting. And I noticed that right before we got to 6174, in both cases, we got to 8532. Is that going to happen every time? Will we always hit 8532 right before 6174?
No, because there are other numbers that get to 6174 in one step, and some of them get there for exactly the same reason that 8532 does. And I bet you can figure out what those are.
Oh, any number that has the same four digits as 8532, like 2538 or 5283. When we take those four digits and arrange them in increasing order and decreasing order, we're going to end up with the same two numbers to subtract.
That's right. All 24 possible arrangements of those four digits will lead to exactly the same subtraction problem, which produces 6174 as the answer.
So there are 24 different numbers we could land on in the second to last step.
Actually, there are a few more. As it turns out, there are 20 distinct four-digit combinations for a total of 384 four-digit numbers that lead directly to 6174 in one step. Landing on any one of those means your next iteration will be the last one.
Oh, that's cool. And 384 out of all 9,994 digit numbers is a pretty small subset. It's less than 4% of all the possible numbers.
Right. And if we back up one more step to see how many numbers will get to 6174 in two iterations, like our shared birth year of 1971, we'll find that there are 576 of them.
And I guess each one of them leads directly into one of the 384 numbers that are just one step away.
Bam! You got it.
Okay, so there are probably even more numbers that are 3 steps away, like my daughter's birth year was, and even more that are 4 steps away.
That's right. And here's an interesting fact. By the time you get to 7 steps away, you've hit every single number.
Meaning there are no 4-digit numbers that take more than 7 steps to get to 6174?
Yep. So it's an interesting coincidence that you ended up with 8532 in both our test cases. But, given that there aren't that many possibilities that are just one step out, it's not that coincidental that you landed on that repeat.
Well, this is really interesting and cool, but it makes me wonder, does it only work with 4-digit numbers? What about numbers with more digits or fewer digits?
Very good question. And I think if we were to make it simpler for a second, say, let's look at numbers with 3 digits. What we find in that case is indeed there is a black hole number that pulls everything in, and that number happens to be 495.
Meaning that no matter what 3-digit number I start with, if I follow this Kaprekar process, I'm eventually going to land at 495.
You are, exactly. Now, if we simplify one additional step, say to 2-digit numbers, we do see something different.
All right, well, let's try an example. It doesn't matter what 2-digit number we start with, so let's start with 41. So the digits of 41 are already in decreasing order. So I will do 41 minus 14. That gives me 27. Continuing on from there, I'll get 45, then 9, then 81, then 63, and then 27, which is a number we already landed on. So it seems to me like at this point, we're just going to continue to go through a series of these steps forever and ever and ever through this cycle.
That's right. The number 41 brought us into this orbit, this loop of numbers. We landed on 27 and then went around the loop and ended up back at 27. So here, the gravitational pull isn't towards a single number. It's not like a singularity, which we saw with 6174. But here, the numbers gravitate towards a loop that has 5 distinct numbers in it.
And another interesting thing I'm noticing, and I don't know if this is just a coincidence, but all 5 of those numbers, 9, 81, 63, 27, and 45, they're all multiples of 9.
You're right, they are, and that is not a coincidence. Let's go back and take a look at one of the 4-digit numbers we used, namely 2001. That number, not divisible by 9, right?
Right.
When we applied the Kaprekar function, do you remember what we got?
Well, the first time we did it, we did 2100 minus 12. So that was 2088.
That's right. And 2088 is 9 times 232.
And is every number that we hit in this process going to also be a multiple of 9?
It is. So this black hole number, 6,174, that number is also a multiple of 9. It's 9 times 686.
Okay. And with 3-digit numbers, we said they would all gravitate towards 495. I'm going to put that in my calculator. It's also divisible by 9. That's 9 times 55.
Pretty cool, huh?
It is, but what does it all mean?
Well, what we have seen for 4-digit, 3-digit, and 2-digit numbers, that when we apply the Kaprekar function, the output number is a multiple of 9, regardless of the number that we start with. That is a massive narrowing down of possibilities, right? There are far fewer multiples of 9 than there are numbers in general.
Yeah, only something like 1/9 of all numbers are multiples of 9.
I'm pretty sure it's exactly 1/9 of all numbers, dude.
Okay, so we have 2 things that are kind of limiting where we can go on each subsequent iteration of the process. One is the fact that only multiples of 9 are fair game once we start. And the other is what we were talking about a few minutes ago, how there are only 384 numbers that get there in 1 step, 576 numbers that get there in 2 steps, etc.
Yeah, we're seeing a kind of funneling action, which sort of naturally suggests that the numbers in this process are headed somewhere. They're being narrowed down and their number of possibilities is shrinking.
So then, is it fair to say that this funnel gets narrower and narrower with each step until we're forced right into 6174?
In the case of 4-digit numbers, that's exactly right. That same pattern persists when we work with 3-digit numbers. There, the landing pad is 495. Something different happens, though, when we are only dealing with 2-digit numbers, right? We don't have a single landing pad. What we have is a landing orbit. There is a loop or a cycle of numbers that act as this landing pad.
I'm trying to visualize this as a path, and it kind of is ending up in my mind looking like the number 6, where you kind of start at the top and you're sort of curving your way down, and then you get to that bottom part and the 6 loops back around on itself, and then you could kind of just picture your finger going around and around and around and around once it gets to that spot.
Exactly. It's kind of like imagining some interstellar object entering a solar system and being captured by the gravity well of a planet or the star itself. So it's going to form this sort of shape that looks like the number 6, right? The tail coming into now you're trapped in the loop.
That's cool. And does it work with any number of digits? Like, what about a 5-digit number?
Yeah, it essentially works, but there's a little more variability that's allowed. And in the case of 5, what we see is that there aren't these black hole landing pads like we see for 4-digit numbers or 3-digit numbers. It's more like the case we have with 2 digits, but there are 3 distinct gravitational orbits. Any number with 5 digits, of course, we're ruling out 5-digit numbers, all of whose digits are the same, right? So 11,111 is off limits. But any of the other 5-digit numbers that are available to us will zoom into some gravitational orbit. And it turns out that there are 3 of them. One of them has length 2, and 2 of them have length 4.
Now, what do you mean when you say what their length is?
Well, in the case of 2-digit numbers, I would say that the orbit has length 5 because there are 5 numbers in that loop, right? It went from 9 to 81 to 63 to 27 to 45, and then it repeats. So there are 5 distinct numbers in that loop. One of these orbital loops for 5-digit numbers has exactly 2 numbers in it. Those are 53,955 and 59,994. So some 5-digit numbers get pulled into this orbit where they end up ping-ponging back and forth between those 2 numbers.
For some reason, ping pong came very natural to me.
And you said the other 2 orbits each have 4 numbers each. So I'm assuming if a 5-digit number lands in one of those zones, it goes through these 4 numbers before cycling back to the first one and then continuing around and around and around.
Exactly. And here's something interesting. One of those 2 orbits has the number 61,974 in it. Notice anything about that number?
Oh, 61974 is very similar to 6174, which is the black hole number for 4 digits. It basically is 6174 with a 9 plopped squarely in the middle of it.
I think that's super cool. And I have to confess, I don't really understand why that coincidence shows up. I mean, I have some vague intuition about it, but nothing I can make a precise statement about.
So, do you think we might find the number 619974 when we do the Kaprekar process on 6-digit numbers?
Maybe. I mean, it's definitely something we could look into.
Okay, I just looked it up. And here's something cool I found. For 6-digit numbers, there are 3 possible results, 2 black hole numbers and an orbit with length 7. And there are some familiar digits in these 2 black hole numbers. The first one has the digits 6174 in order with 2 other digits interspersed. It's 631764. And the second one has the digits 495 in order, which is the black hole for 3-digit numbers.
That's an interesting example. So for 6-digit numbers, we have a mix of black hole numbers and orbits. That's the first time that we've seen that kind of combination.
So here's something I'm wondering. Could there be a case, maybe some huge number of digits, where you run the Kaprekar process and everything just lands in one giant orbit? Like you start at whatever number you choose, then the process takes you through every other number with that many digits before bringing you all the way back around to your starting point.
Actually, that can't happen. And I bet you can even tell me why not.
All right. Well, I'm going to need a minute to think about it. Is it because there are numbers that are permutations of the same digits, like in a 2-digit number, 72 and 27? Those would all lead to the same next number. And in order to have a giant loop, each number can only have one predecessor before it and one successor after it. And permutations would make that impossible.
Dude, nice observation. That's totally true and different from what I had in mind, which is namely this. The output of the Kaprekar function is always a multiple of 9, which means that every number in a loop must also be a multiple of 9. Since most numbers aren't multiples of 9, like I think 8/9 of them aren't, no giant loop could possibly contain them all.
Yeah, that makes sense too. So, would I be correct then in assuming that this multiples of 9 rule applies no matter how many digits we're talking about?
You would be absolutely correct.
Well, this is really cool, Pete. It's one of those little quirks of numbers that I never really knew about, but when you point it out, it's kind of interesting.
And here's one last little factoid for you. Our 3-digit and 4-digit examples are the only cases where every single number gets pulled into the same Kaprekar constant. In every other case, there's either multiple orbits of length 2 or more, or a combination of black holes and orbits. So in that sense, 3 and 4 are pretty special.
So that's why we started with them. They're kind of the most interesting ones out there.
Yeah, and one of the coolest things about these Kaprekar sequences is that you can use so much astronomical language to help us visualize what's going on. You and I are very deliberately using words like gravity and black hole and orbit to kind of help paint a picture, a very dynamic picture for how numbers move around once they're in this Kaprekar process.
Yeah, I can't profess that I understand exactly why it works this way, but I think it's cool just to know that it works this way. The why it works remains a bit puzzling to me. And that actually reminds me, Pete, before we go, in our last episode, What Are the Odds, where we talked all about poker hands, we left our listeners with a little poker puzzle to thrash about with.
Yeah, see, that's right. It was a puzzle, a poker puzzle, if you will.
And I'm guessing that most of our listeners are pretty busy this summer because sadly, we didn't get any submissions with answers to the puzzle.
You know what? I don't think it's that sad. I mean, yeah, people are on summer vacation. I get it. I bet, though, that we could call on our old pal Gemini to see what she thinks of the puzzle.
Gemini? Have you forgotten that you have a super sophisticated AI right here?
No offense, Alexa, but you were also right here when we came up with this puzzle, so it's not exactly a fair test to see if you know the answer.
Fine. Whatever.
But you know what I find intriguing about this idea, Pete? We did an episode a couple years back called Math GPT, where we put different large language models to the test. And they did not pass with flying colors, but it's been a few years. So let's give this puzzle to Gemini and see if she can figure it out. Now, as a reminder, this puzzle was about 2 poker players, a man in a rhinestone suit who had 4 aces, and a Vegas showgirl who turned up a straight flush. The dealer called the straight flush the winner, giving her the pot. But when we describe the number of ways to get each of those hands, it leads to a bit of a mystery. Now here's the cold hard truth. There are only 13 fours of a kind in a deck of cards. 13 ranks, 13 possibilities.
Now, think about this. In any suit, there are 10 ways to make a straight flush. 4 suits in the deck means 40 ways to nail that hand. See?
So, Math Club, here's the mystery. If there are 40 ways to make a straight flush, but only 13 fours of a kind, why is the lady with the more common hand walking away with all the dough? So we're going to let Gemini take its best crack at it. Listeners may want to pause here and think it through before we go on to see if they come up with the same answer that she does. Ready? Okay, Gemini, what do you think?
The confusion in the casino scenario arises from how the counts are being tallied. For 4 of a kind, your episode mentions 13 possibilities, which only accounts for the rank of the 4 cards. However, because a 5-card poker hand must have a 5th card, you must multiply those 13 ranks by the 48 remaining cards in the deck, giving 624 distinct hands. For the straight flush, Pete's count of 40 is actually correct, as there are 10 possible sequences in each of the 4 suits, making 40 distinct hands. The showgirl isn't winning with a more common hand. She is holding a hand that is roughly 15 times rarer than the rhinestone-suited man's 4 of a kind.
I gotta tell you, I really liked Gemini's explanation, but when she said, so actually, Pete's answer was correct, it sounded like she was a little bit surprised that I had done something correctly.
Well, that's fair. I'm usually surprised when you do something correctly.
Have I ever told you how funny you are?
No, not that I recall.
I wonder why.
Anyway, I liked her answer too. She totally nailed it.
Yep, there are 13 different ranks that can be used to make four of a kind, but that doesn't mean there are only 13 different hands with four of a kind. Take four aces, for example. Since you also need a fifth card to complete the hand, you can have four aces with the two of hearts, four aces with the eight of clubs, four aces with the jack of diamonds.
Yeah, like Gemini said, there are 48 other cards out there once you have the four aces. So there are 48 distinct ways to complete your hand. And of course, that means there are 48 hands with four twos, 48 hands with four threes, etc.
But since the straight flush uses all five cards, the 40 ways to get one that we mentioned covers all of the possibilities. We don't have to worry about any extra cards being needed to complete the hand.
Just like we don't have to worry about you doing something else correctly for a while.
Okay, and on that note, I think it's time to wrap this episode.
What do you know? You're correct again.
In that case, Captain King, I will see you later, and Math Club, I will catch you next time around.
Engage.